Alright, so this week I'm going to be talking about stellar evolution. I talked a lot about the main sequence, and I referred to stars leaving the main sequence, their main sequence lifetimes. But what happens when they leave the main sequence? That's what I'm talking about now. So, to start off, some quick an establishing of terms real quick. For the purposes of this assignment, this topic, I'm classifying stars into three categories: low mass, medium mass, and large mass. And I'm defining them as follows. Low mass stars are less than 8 solar masses. Medium mass stars are from 8 to just under 25 solar masses. And large mass stars are 25 solar masses or greater than or equal to 25 solar masses, where a solar mass is the mass of our sun. It is defined relative to our sun, so our sun is 1 solar mass by definition, and then like a star that was twice the mass of the sun would be 2 solar masses, and so on. Now, the assignment that you're going to be doing for this week kind of confusingly uses a little bit of a different notation, which calls medium mass, what I call medium mass stars, it includes in the large star category. So when it talks about large stars, it's talking about both medium and large stars as I describe them. And the reason that I've split them up into these categories is that what happens to stars when they leave the main sequence depends on which of these categories they're in. Now, these cutoff points in terms of mass aren't really precise. For instance, there are some people who think that the low mass cutoff point should be more like 10 or 12 solar masses. But for the sake of this, we're just gonna go with these numbers. Alright, so I'll start with low mass stars. What happens to low mass stars when they leave the main sequence? Well, first, what does it mean to leave the main sequence? The defining feature of a main sequence star is that it is burning hydrogen into helium through nuclear fusion in its core. Stars leave the main sequence when they run out of hydrogen fuel in their core to burn. So, what happens then? Another concept I've referred to recently, hydrostatic equilibrium. Stars can hold their size and shape up against the inward pull of gravity because their internal energy, the heat that they produce, and the heat that they have in their molecules and atoms and stuff, creates an outwards energy pressure, which opposes the inwards pressure of gravity and reaches a balance. Another contributor is the light that the sun produces. Light can also apply a pressure when it hits something. I understand that that's very weird and counterintuitive that light could apply a pressure, because light doesn't have any mass, but I kind of ask you to just take my word for it, that yeah, light can apply pressure. And so the light that the sun produces in its core also contributes an outward pressure to balancing out with gravity. So what would happen if a star stopped producing energy in its core? Well, now it would quickly lose its ability to hold itself up against gravity, right? And this would happen first in the core. So here's what happens. When a main sequence star runs out of hydrogen to burn, doesn't have enough hydrogen anymore, its core will start to collapse very rapidly. It'll start to constrict into a smaller, denser shape. However, as it does this, it's getting hotter, and it's getting to higher pressures. And so, this contraction will actually allow it to start burning hydrogen again. But not in the same way as it did before. I'm going to draw, and this is part of a broader explanation of what happens to low-mass stars when they leave the main sequence. But I'm going to draw a little cross-section of the core of a star which has just left the main sequence. See, the insides of the core no longer have enough hydrogen to burn, really. But there are some areas on the exterior of the core, which for a variety of reasons that I don't fully remember, but also is a little bit beyond the scope of this class, that do end up burning hydrogen after it contracts and gets to this new level of temperature and pressure. So an outer shell of the core is now burning hydrogen, but the inside of the core is kind of inert, right? This is the beginning of a process called shell burning. Now, when a star begins shell burning, it becomes a giant, usually a red giant. Certainly a red giant in the case of low-mass stars. Sometimes it's like a blue giant when we get to like large-mass stars, but I'm getting a little ahead of myself there. Now, the reason why shell burning causes stars to become a giant, like honestly, I don't even know. Like, it's some kind of a very complicated interaction of various things going on. I'm not going to get into it. So just take it from me. Shell burning causes a star to become a giant, usually a red giant. Like a little arrow to show that it causes it. Okay. So, but let's get back to the core. So here's the core. Now you can imagine that as this shell on the outside is burning hydrogen, it's making a bunch of energy, and it's going to heat up this part on the inside, right? And so as it's doing this, eventually, you're going to get a part in the middle where it gets hot and pressurized enough to start burning helium instead of hydrogen, right? The core has plenty of helium, but it's never been able to burn helium before, but it can now, right here in the center, right? And now it's got another source of energy, the hydrogen shell on the outside and the little bit of helium burning in the middle. Now, this is something that I'm not going to draw because it's kind of hard to draw, so I'm just going to kind of describe it and then draw the end state. So you can kind of imagine that since it getting to a point of, you can kind of imagine, I think, that as the temperature of the inside of the core increases over time from the hydrogen burning going on around it, that the amount of the inside of the core which is able to fuse helium would get bigger over time as it got hotter and hotter. And so what happens is that it grows out until it reaches where the hydrogen burning is happening. So, eventually this whole inner part is going to be burning helium. Now when this happens, it causes the inside to become even hotter and more pressurized, right? And eventually we're going to get another thing happening. At the center, now, helium is able to fuse into carbon, right? So we're forming a new shell. And by the same process, the carbon will start small and then grow out until it starts to approach the helium shell's boundary. And so we're going to have 3 shells. Hydrogen, helium, and then carbon in the middle. Now, for some low-mass stars, this is as far as shell burning gets. I believe our sun, is just going to get up to carbon, and then it's going to stop there. However, some stars that are at the high end of the low mass range, your 7 solar mass stars and stuff like that, may be able to get 1 or 2 more shells going. In any case, the rest of the process pretty much goes the same for all low mass stars. Now, being a giant for an extended period of time, which low-mass stars are, the amount of time a low-mass star is a giant is quite small compared to the amount of time that they were a main sequence star, but still pretty long. And so when they're a giant for long enough, the core will sort of lose hold of the outer layers of the star. And those outer layers will kind of become diffuse. They'll stop being part of the star and they'll just sort of fly off. And this creates a planetary nebula. Are formed by gas that used to be part of a star, but the star went giant for a long time and it just kind of dissipated. Now it's a nebula. But the core remains. And the core remnant that's left over after the outer layers of the star have become a planetary nebula is called a white dwarf. White dwarfs are very small, oftentimes on the order of being the size of Earth, right? But they're very dense, very, very dense. White dwarfs can also be very hot. As you may recall, they share a spectral type with like the biggest, hottest main sequence stars. But white dwarfs generally aren't really producing very much energy themselves. So they're pretty much just a hot thing cooling off. They don't have the ability to stay hot forever. Now, what else is there about white dwarfs? There's something else. Oh yeah. Now you may be thinking, Cooper, you said that stars can hold themselves up because of their internal energy production, creating an internal pressure to oppose the inwards gravity. But now you're saying that white dwarfs don't have that? So how do white dwarfs keep their shape? Great question. White dwarfs are held up not by internal energy pressure, but by something called electron degeneracy pressure. Basically, electrons sort of have the property that they don't want to be in the exact same state or situation as other electrons that are near them. So this does include position, right? Like, oftentimes electrons aren't going to want to be in the same spot, but it's not just position. For instance, electrons have a quality called spin. They can be spin up or spin down. And so it would actually be okay for electrons if they were both in the same place and one was spin up and the other was spin down. But if they're both spin up and in the same place, that's a problem. Electrons sort of resist that. And the word degeneracy in this comes from, in quantum mechanics, degeneracy means two things being in the same state. So electrons resist being in the same state as other electrons that are near them, and this resistance creates a pressure, a very strong pressure, which is what holds up white dwarfs. So, I believe that about covers low mass stars. In the next video, I'll be talking about medium and large mass stars.